Coming back, and we're going to continue the afternoon session on the same theme of optimization and control. So our first talk this afternoon is by Professor Andy Sutton from the Georgia Institute of Technology, where he's based in the Industrial Systems and Engineering option. Andy and his group have won and been nominated for several awards in the general area of optimization, including Andy received the 2018 NSF Career Award. His research interests are in typically really tough non-convex optimization problems, and he's interested in both application and theory. And today, we're talking about theory and application with respect to power systems.
Okay. Thank you, James, for the introduction, and thank you, organizers, for inviting me here. It's really great to be here for such a wonderful workshop. I'm going to talk about some of very recent work that we're doing on distributed optimization, motivated mainly by the power system, the tough problems in power systems, non-convex ACOPF and related issues here. The topic is I'm going to present some new algorithms, called two-level distributed algorithm for general constrained non-convex, could be non-smooth optimization problems, and I'll also focus on some applications in power systems. So this is my joint work with my PhD student, Kai Zhao. First I'm going to give an overview of distributed algorithms for non-convex problems, and the key thing here is to consider constraints, especially complicated constraints like the power flow equations in power systems. I'll review some of the existing algorithms, especially based on ADMM, alternate direction method of multipliers, for non-convex optimization problems, and to point out some intrinsic, I would say, difficulties, or I use a strong word, contradiction here. I'll show you that some of the key assumptions that needed for convergence of such algorithm actually cannot be satisfied when you have complicated constraints. So that point out sort of issue with the ADMM framework, and sort of raised the question how to guarantee convergence for non-convex problems if you want to do distributed computation. So then we'll propose a two-level algorithm that sort of go beyond the framework of ADMM, that can guarantee both local and global convergence for non-convex problems. And I'll show some of the key ideas there. And then we'll talk about some applications in ACOPF. And the algorithm is pretty general for non-convex constraint problems, so it can be applied for other applications that I'll talk about, optimization over compact manifolds, or certain non-smooth problems that can also be solved using this framework. Okay, so here is the sort of motivation for our study. So we want to look at a general sort of network flow problem. You can think about this as ACOPF or other constraint problems on network, where each node here has a decision variable, which can be a vector, and each decision variable at a node has its own local constraint set, big Xi's, and also every node has coupling constraints. For example, Xi or node I has a Gi constraint that involves the variable Xi and also adjacent nodes decision variables when they're connected. So this is the constraint optimization problem, where we have a decomposable or summable objective function where each node has its own objective function, and we're minimizing the sum, subject to local constraint at every node and also coupling constraint. So the question is, if we want to do distributed computation, meaning every node solves a local problem that involves local variables, and maybe passing messages or computational results with its adjacent nodes, and jointly solve this problem. Of course, this problem here can be non-convex, both in terms of objective function and especially constraints here. So the goal is to design a distributed algorithm on solving this kind of problem. Of course, when I say solve this, if it's a non-convex problem, I'm talking about stationary points, KKT solutions. So you can see that ACOPF is such a problem that I'm also going to formulate more explicitly. And also more sort of abstractly, if you have a constrained problem, as I'll show later, you can sort of always write the constrained problem as a network or represent the variables and constraint as a network and write the problem in this format. So it's pretty general setting. So here is the OPF problem. I think I don't need to go into details here, but just to point out the structure here that we have a objective function that's sum of cost over every node I, and each node could have a generator there. And the nodal constraint here involves the nodal variables that have real reactive power of generation and real and imaginary parts of the voltages at every node. And this set, the nodal constraint, feasible region, can be voltages constraint or generation constraint. And the coupling constraints at every node are the power flow equations. For example, here, this node I has power flow equations that involves all the adjacent nodes variables. And you can also have flow constraint here. So this is a specific example showing ACOPF is a non-linear network flow problem with pretty complicated constraints, as previous talks already described more rigorously. Or this kind of general constraint optimization problems, if we have variables here, here I write it as summable objective and constraints here, then you can always represent this as a graph with variables and constraints, and they are connected if this constraint involves the variables here. And the question here is, if we want to do a distributed optimization or computation to solve this kind of problem, how should we do that? I think there are a couple key questions. One is, how should I reformulate such a problem in a way that it's easier for distributed computation? And other question is, of course, if the constraints are non-convex, then can we guarantee convergence? So there is a rapid development of this distributed algorithms in the past few years, especially for non-convex problems. So there are some general fundamental principles that's already been described before on Lagrange relaxation or augmented Lagrange relaxations that we'll see it's going to be the fundamental principle here. And there are recent results. I'm going to go into some of the details here later on convex optimization. So even for convex optimization, it's not guaranteed that the convergence will be achieved. You need to have some assumptions on the properties of the objective function constraints and constraints. And in the non-convex optimization part, it's even more challenging in terms of guaranteeing convergence to KKT point, for example. And there are many applications, and especially even in power systems, there are a lot of recent work on solving ACOPF, for example. But what I wanted to point out, especially later I'll give you examples, is the formulation or reformulating a constraint problem into a formulation that you can use this algorithms is actually a challenge, especially if there are complicated constraints. It's actually not that easy to figure out how to reformulate the problem. So I'll first very quickly introduce the ADMM framework. I think many of you here are very familiar with this. And then I'll try to point out some of the intrinsic difficulties with the ADMM framework for constraint problems. So this is a basic ADMM framework. So if you read a paper on ADMM, usually they start with this formulation. So basically you have a optimization problem that involves two variables. So sometimes it's called two-block ADMM. So the first block is x variable, the second block is z variable, and you have an objective function of the sum of the two costs, and subject to linear constraint here. So this is a coupling constraint that couples the variable x and z, and it's a linear coupling constraint. And each variable can have its own feasible region. So usually the ADMM literature starts with such a formulation. So assuming that you already have your problem, for example, in the nonlinear network flow problem that we started with, somehow you have to reformulate that into this framework. And then once you have this formulation, then you can apply the so-called two-block ADMM iteration. So essentially, if you look at this, this is exactly the augmented Lagrangian that we have the original variable, original objective here, fx and hz, and this is the Lagrangian term, and this is the augmented term. So the ADMM is an iterative process that every iteration, you first fix the do variable and the z block in the previous iteration's value, and only optimize over the x variable. You get x update, and then you use the x updated value and the previous iterations do variable to update the z, and then you update the do variable. So this is the gradient ascent step for the do variable. So this is the ADMM framework. Because of this sort of Gauss-Seidel iteration that you fix one variable, optimize the other, this becomes separable in terms of the variables. So you can do distributed optimization for the individual variables. So this is two-block because I have x and z two variables. More generally, you can have a multi-block ADMM. So here I have, let's see, I have x0 all the way to xp. These are p+1 blocks. And also I have last block z. So I have p+2 blocks here. And the objective, again, is a sum of the individual block variables objective. And the constraint here is a linear coupling between all the variables. You could have a non-zero vector here also, but I write a 0 just to make it simpler in notation. And every variable has its own feasible region. So the multi-block ADMM is again forming this augmented Lagrangian function. So here I write all the x blocks into an x variable, and this whole part here over the x, I write it as ax, and then plus bz. So here can be 0, for example. Actually should be 0. So this is the augmented Lagrangian function, and then the multi-block ADMM is just going through the variables block by block. Right? For example, for the ice block, all the previous blocks have already been updated, and the ones that after the ice block has not been updated, so you update xi block, and then keep sweeping through the x variables, and then you update the z variable, and then you update the y, which is the do variable. So here I singled out the last block, the z update, because later you see that in order to guarantee convergence, the last block actually is special. So there's some special requirement on the objective function of the last block in order to guarantee convergence. So this is a multi-block ADMM. And this structure or this algorithm can be applied when you have a convex problem or you have non-convex problem. So there are many convergence results. Here is one that's quite general. So this is a multi-block ADMM that we just, or this is the formulation that we just described. Again, usually all the papers on ADMM will start with some formulation like this and prove convergence. So for example, linear convergence can be established for convex problems if there is a global optimal solution and strong duality holds, which is not, in general, not guaranteed, but if you assume that's the case for this convex problem. For example, this f variable here is decomposable, further decomposable into sum of two functions here, where the key thing is you have to have some assumptions on the function. For example, the g's here need to be strictly convex and continuously differentiable and has a Lipschitz continuous gradient, for example. That's needed. And this hi here needs to be affine function. So that's the requirement on strictly convexity and linearity of the objective function. And also you need to have some assumption on the matrices here. So for example, all the matrices have full column rank. That's a typical assumption. Oh, I didn't write the individual constraints. For every xi, the feasible region need to be compact and linear, for example. So this is a typical set of requirements for convergence of ADMM for convex problems. And later you see that there are simple examples where ADMM will diverge even for linear programs. Everything is convex. For non-convex program, there are also recent progress, very promising progress in terms of, again, this setup. So if you have already formulated your problem into this model, then you can look at the convergence. So here I didn't write xi in big set xi because you can write that as an indicator function into the objective. So here this objective could be non-smooth. So here is a set of conditions proved in this paper. For example, the feasible, the problem is feasible, which again is not a guaranteed property. So you assume it is feasible, and the objective function, this function is coercive, meaning it is some regularity conditions. I want to point out some key assumptions here. The first one is the image of A. Again, this A matrix is the concatenation of all this A0 up to AP for the x variables. So you put them together as a big matrix, and then you look at that matrix A versus the last block's matrix B. A key assumption is the image of A has to be contained in the image of B. So that means whatever variable x you have here, you put any variable values here, there should be a variable z such that this equation can be satisfied, right? So that's the meaning of image of A is contained in image of B. And then there's some, again, regularity conditions, smoothness conditions on the objective function, where there are Lipschitz smooth differentiable conditions on G and lower semi-continuous. So this Fi, as I said, could have an indicator function in it, so it doesn't have to be smooth. As long as it's lower semi-continuous is fine. So your feasible region is closed. That's okay. And here is another key assumption. So it says the last block's objective function h, which is the objective function of z, this function has to be Lipschitz differentiable. So this function cannot be non-smooth, this last block. Okay. So this immediately implies you could have constraint in the x variables and embed that constraint into the objective function using indicators. But you cannot do that for the z variable. Okay. So later I'll show examples. Once you don't satisfy this A2 and A4 assumptions, this ADMM can diverge. Okay. And later I'll show you that these two assumptions sort of contradict with each other if you don't have a problem already in this form. Say you have a nonlinear ACOPF problem, you want to formulate that into this form, and then you actually run into intrinsic problems with these two. You cannot satisfy these two assumptions simultaneously. Okay, so there are some other more technical assumptions, but the key thing I want to single out is these two assumptions. So here is some very simple looking problems. For example, this is a linear program that you minimize 0 subject to this one linear equality constraint, and you have 3 blocks, x1, x2, and y, and you apply ADMM multi-block, 3-block ADMM on this, and it will diverge. So it doesn't satisfy some of the key assumptions before. For example, in this case, the objective function is not strictly convex, and the feasible region is not compact. So that causes issue. Even though this is a very simple LP, it's just a feasibility problem. Here's another problem here where you want to minimize x1, x2. These are indicator functions, and x1 should be equal to x2 essentially, right? If you apply ADMM on this, again, it will diverge. So here the set is actually non-convex. Okay. So for this case, you see that for both cases, this assumption is not satisfied. The image of A is not containing image of B. For this case, it's quite easy to see, and for this case also, the image of A is the coefficient matrix for x1, x2, and it is not containing any image of B. So basically, that means I can't have some x1, x2 such that there's no y to make this equality, two equalities, satisfied, because you can have x1 not equal to x2, right? So so that shows this assumption actually is quite critical for ADMM type framework to converge. Here is another problem here. Again, it's quite simple. It minimizes the negative of the absolute value of x plus absolute value of y, and subject to x equal to y. And you can also put a compact set over x, right? So this problem satisfies all the assumptions in the previous slide. In particular, the image of A is of course containing image of B here, but ADMM still diverges here because it doesn't satisfy the A4 assumption, meaning the last block y, its own objective function is not smooth. Okay, so if you apply ADMM on this, what would happen is, for example, you start from this initial point, it's going to oscillate. The even iteration will always have this solution, where the odd iteration always had this solution, and even iteration have this solution. So it never actually converges. So that's some convergence properties of ADMM, and this sort of in existing literature, this is sort of the most general conditions under which ADMM could converge for non-convex problems. All right, so if we go back to the nonlinear network flow problem, if we want to do some distributed optimization on this, the question is, can I directly apply non-convex ADMM on this? There already established convergence result, as I showed earlier. Right? The question is that applicable here? So as I said, all the previous work will start from a formulation like this. So you already have a formulation in this linearly coupled way, and then apply ADMM on this. But the question here is, I have something like this. I have a minimization problem with coupling constraints, and there's an underlying network here. So in order to do distributed computation, I think a necessary step is to reformulate this such that every node, if I want this to be an agent, then I need to duplicate variables at this local node of its adjacent nodes variables. For example, at xi here, the node I should have xi, its own variable, but also it should have a copy of its adjacent nodes, xj's variable and xk's variable. So in this particular way, I'm formulating this copy in this way, so I define a set of variables x. These are xi is the original variable, and x super ij means it's xi's copy of xj variable. So that should be equal to xj. So I'm introducing another copy here of the x bar variables. These are the x bar I, x bar j, and x bar k. So these are the original variables essentially. And then the agent or node i's copy of j should be equal to j's own variable. And at j, xj should be equal to x bar j. So then this forces consistency between the copied variables. This is one way to formulate this copying, but no matter how you do it, you have to duplicate variables so that you can do distributed computation. This way has a property of parallel decomposition, because every node every node has a set of variables. For example, node I has a set of variables with superscript I and all the adjacent variables. So once I fix the bar variables, right, if I fix the bar variables, then the nodal problem is decoupled. Xi's problem or node I's problem is not coupled to node J. For example, if you look at the constraint here, right, the node I's constraint only involves its own local variables. The coupling is right here. So if I fix the bar variables, then all the nodal problem decouples, right? So then you can do parallel computation. So so that's one way to duplicate variables. You could also duplicate variables such that maybe part of the network, for example, this two can be parallelized, but this system and this system need to be updated in sequence. So you can do different ways to do parallel decomposition or serial decomposition or mixed decomposition. But the bottom line is, no matter what way you do, you have to duplicate variables. Okay. So you have to introduce constraint like this that duplicate variables. However, once you duplicate variables, you see that you're going to violate the key assumptions there. So again, this is the duplicate constraints. That again, this is linear couplings between the original variable and duplicated variables. But if you write it in a matrix form, it's going to be something like this. You have a variable x, right, that contains all the local variables at every node, and then you have this x bar variables, such that the corresponding variable would be forced to be equal. But then you have a matrix which is identity here, and another matrix which looks like this. So, and if you look at these two matrices, they do not, at least the image of A is not contained in the image of B. Okay, the image of B is contained in the image of A, but not the other way around. Okay. However, if you remember, there are two key things, right? The image of A needs to be contained in the image of B, and the last block, which is the B block, has to have a smooth objective function. So here the x variables are constrained, where the bar variable is not constrained. So you cannot, essentially, either you put this unconstrained block as the last block, then you have to violate the image constraint. Or if you don't put this in the last block, then the last block would have constraints. So you wouldn't have smooth objective in the last block. So these two things you cannot actually satisfy at the same time. So if you already have a linear formulation like this, you may be able to have it. But if you start from an ACOPF or some general constraint problem, you actually cannot satisfy this because you have to do duplication. So the duplication itself introduces this constraint with this kind of structure. So that's that's sort of the intrinsic contradiction of, if you want to apply ADMM, and we see that these two assumptions are critical, but you just cannot satisfy them at the same time. So so this sort of indicates that the ADMM framework by itself is sort of limited in terms of dealing with general constraint problem. So if you look at the successful cases of ADMM for computation, usually it's very successful, for example, dealing with unconstrained problems, or problems that only have linear constraint with only this coupling constraint. Essentially, you have a couple problem, for example, in the objective, and then you can introduce new variable copies so that your objective is decoupled. So then you only have linear equality constraints. So that's the cases where the ADMM framework will be successful. This intrinsic two assumptions can be satisfied at the same time. But once you have complicated constraints, like in power system or other engineering system, you cannot avoid handling those constraints. So then it looks like the ADMM framework is limited. So this motivates us to look at, how should we actually guarantee convergence? Because here is a divergence behavior of ADMM. I think if you have tried ADMM, you probably see something like this. This is 300 bus system partitioned into two subregions. This is simulation of the augmented Lagrangian function value. It looks like it's converging, but actually the residual of the coupling constraint is not. So it is not converging to a feasible solution, and it can easily diverge or oscillate. So, and this exactly because these two assumptions are not satisfied. Okay, all right. So we sort of need to go beyond the ADMM framework or modify it somehow. So that's the motivation. The key idea here is, I think most of the existing work happens to deal with unconstrained problem. And then it really makes sense to directly start from that linearly constrained formulation and just work on that. But here, once we have complicated constraints, you sort of need to reformulate first. So I think the first key idea is to reformulate that problem into a way that we can apply ADMM in some way. So the way that we do it is very simple. We introduce a new variable. So this is a new block. It's a slack variable, and I make it 0. So of course, it's not changing the problem at all. But you see that if this z is a new block, then I'll have 3 blocks instead of 2. And this last block is not constrained. It doesn't have an objective function. Okay. And then we wonder if we can directly apply ADMM on this with 3 blocks, it won't work. Again, because of the image constraints is not satisfied. So then what we do is, so this image constraint is not satisfied here. So we need a 2-level algorithm. So essentially, in the inner level, I'm going to introduce a z variable here and make z equal to 0, but I'm going to relax this z equal to 0, okay, into the objective in the augmented Lagrangian way and drive the z to 0 in the outer level. And then in the inner level, I'm going to solve this remaining problem here in 3 blocks. And the last block has this special structure of a identity matrix, so the image constraint is satisfied. And the objective has, I can control what the objective for the z block is in terms of augmenting term. So this 2-level algorithm looks promising. So here is more details here. So I relax the z equal to 0 in the objective, in augmented term, and the inner problem will solve this. And the outer level will drive z to 0. Okay, we'll update the lambda variables and drive this to 0. So more specifically, this inner problem, again, I'm going to relax this right in the augmented Lagrangian way and apply a 3-block ADMM on this. So there will be another do variable associated with the inner problem constraint, but this lambda k is the outer lambda. So in the outer level, I'm going to only update lambda and try to drive the z to 0. Okay. So the image constraint is satisfied in the inner problem because I have an identity matrix here. And because the Lagrangian, augmented Lagrangian term, as the previous talk pointed out, this is the simplest one that you can add to the as an augmented term, and it's a strongly convex function. So the last block would have a strong convexity and smoothness and everything. So that's nice. But the thing is, now I have 2 levels. So the inner one is a non-convex problem. I need to solve this by ADMM. But I cannot expect that ADMM can solve this to global optimality. So I have to, if I want to have convergence, I need to prove that the overall 2-level framework would still converge to a stationary point, even if the inner level is only solved to KKT point, for example, which is believable. I think that's sort of reasonable to expect, and it is the case. So the inner level will solve this problem in a distributed way, and using ADMM, with 3 blocks, and the outer level would just update the lambda variable. Okay. So it's sort of a mix of ADMM with a augmented Lagrangian framework to have these 2 levels. So if you look at the specific subproblems, actually, since we're duplicating variables, the x bar variables, so you would have a lot more variables depending on the structure of your network. But the good thing is 2 subproblems. So these are 3-block ADMM, right? Solve x, solve x bar, and solve z. This x bar problem and z problem have closed form. So you don't really need to do any numerical computation here. So the only problem is on x, which is the original variable. So it's not too much a scaling of the problem. So the assumption for convergence here is the following. So it's actually quite general. We don't need smoothness in terms of the objective. The original objective function we assume is continuously differentiable, but the constraint does not have to be a smooth constraint. Here I assume the original problem is feasible, but later we can also devise some way to actually detect feasibility. So even if your problem is infeasible, we can run the algorithm to actually detect if it's feasible or not. And we assume the inner problems, this subproblem can be solved. As I said, this is a non-convex problem by itself, so we cannot expect to solve to global optimality. We only assume that you can solve this such that the next iteration is at least as good as the previous one. So that's a mild assumption. So based on these assumptions, we can prove that this 2-level algorithm would always have a limit point, and in convergence, and that limit point, if along the subsequence converging to that limit point, the y's is the do variable sequence has a limit point, then we can show that the limit point that converges to is a feasible stationary solution, and the existence of limit point on the do variable sequence can be guaranteed by some constraint qualification. So basically, this 2-level algorithm sort of converges as expected. So let's see. I guess I'll skip of the proof ideas. Basically, to prove that the inner level problem would converge to certain stationary point. Usually in the literature, because it's only 1-level ADMM usually in the literature, so they usually prove they assume the subproblem need to be solved to optimality, to global optimality. But for this 2-level thing, the inner one, we cannot sort of assume that. So we could prove that the inner level problem will converge to a approximate stationary point, and then we can prove that the sequence of the inner, when you run the ADMM, when it converges, every time it will give you a point, so that will give you a sequence of inner solutions that has a limit point, and then we can show that the limit point is a stationary point of the overall problem. So I'm going to show you some applications for ACOPF. It's still very preliminary results. So again, this is the ACOPF basic formulation in the rectangular coordinates. So again, you can look at this problem in this nonlinear network flow framework. So we partition the network into subregions here, and the interesting thing is basically you have a network, a power grid, and you have to somehow partition it into a new network, sort of a induced subgraph of your original graph. That graph, it matters for convergence, not the original power grid. So let's see. So again, this is the one-level ADMM, and here are some results for two-level. So I tested 14 up to 300 bus systems with different number of partitions or subsystems. For example, these are two subsystems. One has 5 buses, the other has 9 buses. For example, there are 3 tie lines. So here is the number of total inner iterations. So how many iterations that the ADMM in the process of convergence, how many total number of inner iterations is solved, and this is the outer level iteration. So this essentially tells you how many times a ADMM is actually solved. So the number of outer iterations is not that big actually. And this is the gap in terms of optimality gap when it converges. And this is the residual, so this is feasibility. And this is the computation time. So I think this is the parallelized time that when we implemented this. So for example, for 300 bus, if you partition the system into 4 different regions with 11 tie lines, it can still converge in 30 seconds. So we're still testing on larger systems, and also it's not quite clear to us how to actually optimally partition the system if you do have that sort of liberty to do it. So what is the property of convergence with respect to the structure of the graph, for example? I think we think it's related to some sort of spectral property of the Laplacian of the graph, or conductance of the induced graph. But we're still working on that. As I said, this framework is quite general for constraint non-convex problem. So we look at some optimization problem, for example, pretty nasty polynomials over some spheres. So that's a compact manifold. So our algorithm can guarantee convergence. And essentially, this is the sort of the first algorithm that could guarantee convergence in many of these ACOPF. In this problem, as I said, linear programming, we already see an example where there's only 3 blocks ADMM would diverge. So under our framework, it will converge, a guarantee to find a solution or detect infeasibility. Or non-smooth problem. This is the same problem that showed divergence of the original ADMM. Our framework will guarantee convergence. We did an interesting test on sort of a larger scale system where minimize this kind of objective function here with respect to a compact manifold of a sphere here. I think this is related to minimizing some energy function of point configurations. So we want to compare with a centralized formulation solved by IPOpt. So IPOpt is one of the most popular or really most efficient non-convex solvers. So we scale up the number of variables here and look at the objective function and time. And compare to our proposed 2-level algorithm. And you see that what is promising is the time actually of the 2-level distributed algorithm actually beats the IPOpt centralized problem, centralized solver. Sorry. And the optimality gap is reasonable, I'd say. And it finds a reasonably feasible solution. All right, so we propose this globally convergent distributed algorithm. We can also prove some local convergence, linear convergence when it's close to the local solution. I think this is one of the first convergent algorithm for general convex, non-convex constraint problems with could be smooth or non-smooth problems. And we're looking at incorporating integer variables. So you can think about if it's a binary variable, you could incorporate x squared equal to x as a constraint. So everything could be smooth, and you can fit that into this framework. But that usually doesn't work because for integer variables, every point, every feasible solution is stationary, essentially. So you find a stationary solution, but that's sort of meaningless. You just basically find a feasible solution. So I think integer problem is sort of another beast. It's how to solve that is an interesting question. I think we have some idea of doing that, and also how to achieve global optimality by either do something with the duality of integer problems or some cutting plane algorithm. Another interesting direction is to, as I said, study the convergence rate of this algorithm, especially in relation to network structures. There's some existing work on convex ADMM on network. The convergence rate can be bounded by the second smallest eigenvalue of the Laplacian, or the conductance of the graph. So if a graph is more conductive, then the convergence is faster, for example. Not sure for the two level, because the ADMM is only just the inner one, so you also have an outer level, so it's not quite clear. And also some parallel implementation. I think that's it. So there's some reference that we just finished the paper. And if you're interested, we do have some recent work on solving ACOPF with global optimality by looking at some minor reformulation of matrices. I think that's by itself is interesting way to reformulate a rank constraint problem. You can formulate a rank problem constraint into a set of bilinear minor constraints. And the bilinear constraints are easier to deal with if you want to do relaxation or branch and cut. So yeah, thank you.
Any questions for Andy?
I was interested in the ACOPF partitionings of the graph. Did you manage to what would happen if you just chose random partitions and took statistics of
that's a good question. So we're still experimenting on that and trying to sort of figure out a principled way to do it. So in the beginning we thought, okay, if you have two if you partition, say, into two subsystems, maybe you want to sort of partition into two subsystems with equal number of nodes and minimize the number of tie lines. So then you minimize the duplicated number of variables. But then this sort of contradicts with the existing wisdom of maybe you want to actually maximize the conductance. In the sense you want to sort of maximize the number of tie lines that connecting two subregions with the ratio of the number of nodes in it. So I didn't show it here. It does look like if you maximize the conductance of the underlying graph, it will help with the convergence. But yeah, it's still not clear. If anyone has any better idea, please let me know. So yeah, it's not clear what is the relation between these two. But it does look like it could be sensitive to how you partition the system.
So just following on from the partitioning.
Yeah.
Well, once you've got your partitions and you sort of solve them and you pass the variables across each edge, are there any convergence proofs that follow like a gossip algorithm type protocol where you randomly choose edges, solve, and then randomly choose another?
I see. So you want to do a randomized update?
Yeah.
I think there is one algorithm that actually does this kind of randomized update.
Is it in the convex?
It's in the convex. I think it also can work for non-convex case. Yeah.
Yes. Perhaps some idea around the SDP, and so the idea to have this causal expansion to use a click. So
right.
The proposition could be useful in your case, or?
Yes. So yeah, that's a good question. Again, I don't know. So yeah, so the sense is definitely this: how to exploit the structure of the underlying network, especially after you partition, because it's not just the underlying original power grid, but when you partition your system, what really matters is the is a boundary node, and the graph that's induced by the boundary node. So yeah, so we're still trying to figure out.
I have a follow-up question on this SDP you're using ADMM. You can use the same kind of.
Oh yes, yes. You can use ADMM or SDP. Yes,
that they are not
that's
doing
true.
that, or they're able to solve SDP with ADMM very
Yes.
easily. But I didn't.
Right. There's some work.
For me to do that, so perhaps using your idea.
Yes, yes. There's some work. If you have SDP, then it's convex already. So even one level ADMM could work there too. So yeah, there's some recent work on solving large.
But you are duplicating the variables.
Yeah, you do need to duplicate variables. Yes.
So your trick or your.
Yeah, but because it's convex, so it's easier then.
Okay.
Yeah.
You know the projection as well.
Right. Yeah.
So I see a lot of this numerical work done on these IEEE test networks.
Right.
Back in my days of doing transportation work, we would study something called Brace's paradox. I don't know if you're familiar with this, but it has to do with how people behave locally versus system.
Right.
And they would show how this would arise on small test networks, but when people tried to replicate it on a larger network, they couldn't always
I see.
see in theory, some things would be true, but in practice, sometimes things would disappear on a big network. It's so common to run this numerical work on these small IEEE networks, but the real networks are dramatically bigger.
Yes.
Is there any insight, you or anybody else in the audience, of moving from these small test networks to the big networks and seeing whether they have the same empirical properties?
Yeah, so that's a great question. I think many of people here are more qualified to answer that question than me. So yeah, I think there is a movement of exactly that to expand the test cases for power system from very standard small system like 300 is very small to larger systems. I mean, Patrick.
Yes, there is a project in the US from DOE ARPA that is called Grid Data to collect big system to try to have some benchmark.
But people haven't actually done the testing yet.
Yes. The benchmark
I was part of that project. There is a 70,000 bus system realistically reproducing the entire US. You just have to go in Tom Overby webpage.
Yes.
For the active system.
Right. We use that system too.
It's going to be used for the competition, the ARPA competition. But it's ready, so you can get it now, and it's going to be available from Matt Power pretty soon. So.
Right. Yeah. So there are some really large synthesis.
But in other words, these studies of, say, the first speaker this morning had these wonderful graphs of these very small networks and these tests of non-convexities. I can say that the data sets are now available, and so in the coming years we'll start to see maybe this type of work done on these big networks.
That was the intention, right? So they're available on Map Power. You have these cases. You have the smaller pieces like Texas, WEC, and so you can get the whole system. And the intention was also to add Canada. So, but right now you have the entire United States should be available pretty soon, and there are already big cases for WEC and for the Eastern Interconnect, so you can use them.
A very big one from Europe, so 13,000.
But what I'm hearing is we're starting to get the networks, and we'll look forward in the future for
the team from Javad, for example, did some experiment on that. Even Pascal Van Anterick and Carlton, yes.
Yeah, I think they're online. Now.
So some people are able to try to, because our issue is the scalability. It's not only the numerical problem. And on SDP, this is a problem here. It's possible to use SDP in small instances, but when you go to this very large instance, how to implement SDP is an open issue.
And if I may add, there is going to be a function in Math Power that can also create variations of the same network. So you start with a seed network, and it will create similarly statistically looking graphs of the same size. So you can try it on multiple networks, not just one.
If I add here, Warren, I think what you suggested is a phenomenon that probably is related to this what is called a Shapley-Fulton theorem. I'm not sure that whether this is familiar to this audience. Okay, what that theorem suggests is that that theorem is a well-known theorem for non-convexity. What it suggests that for a problem that's separable, you have sort of inseparable terms structurally. When you have a larger system, you tend to see some replication of certain things as a separable things. Then the duality gap basically does not grow with the number. As the number of the separability terms grows, the duality, relatively speaking, is small. And then globally, the problem looks like a convex. Now that theorem is that the smoothness of the problem improves as you have a large number, a large system with separable terms.
And that's what I would expect. These bigger systems tend to be...
Right. I think I basically corroborate what your observation is. I think that's a theorem.
If you want to.
And
What's the name of the theorem?
that Shapley is a Nobel
Shapley.
Prize
Oh,
winner
Shapley.
in economics.
Oh, yeah.
Yeah, he's also OR guru.
Okay, so I think that might be a good time to end this talk and thank the speaker one more time.